Log on, tune in, find out. Another good idea from Cambridge.
We're safe. I turned it off.
You need it because you're being recorded.
Right.
For posterity. About 30 seconds.
I'm just listening to him. Of course, I wasn't very
Get yourself to maybe start getting the thing up. So welcome to the afternoon session. I'm Henry Wynne, and Leanna House is going to talk about assessing simulator uncertainty using evaluations from several different simulators. Leanna was a member of the Markham project. We miss her dearly, and things haven't been the same since she left.
For better.
And some of the other people are still associated. Well, you're still associate member of the Markham project. So some are full members. So, Leanna.
Can you hear me? All right, great. Yes, so today after lunch, so it's all right if we start to fall asleep, I'll forgive you. But after lunch, we're going to talk about assessing simulator uncertainty using evaluations from different simulators. As Henry suggested, this particular research started as I was a postdoc with an grant called Managing Uncertainty in Complex Models. So my collaborators really are Jonty Rougier, wherever he is, there he is. Tough questions will be definitely skirted off to Jonty. He's at the University of Bristol, Michael Goldstein at the University of Durham, and then there's me, who's now at Virginia Tech in Blacksburg, Virginia. All right, so I'm the type of person who likes to really start the talks off extremely basic. So with that, even though all of us are very familiar with the use of simulators, let's just at minimum also establish some common vocabulary among ourselves. So here we are, we're with tough problems. We want to be able to assess complex physical systems. And these physical systems obviously range across a variety of domains. We've heard from Grant with the engines from Pratt & Whitney, right? We have climate science or climate change that we'd like to assess. Possibly galaxy formation. A lot of that is done at the University of Durham, or hydrology, hydrological processes. These are all examples of complex physical systems that we're trying to assess using data. And oftentimes, we're stuck with the fact that observed data, real-world data, is just not enough for us to be able to make inferences about these complex systems. So we turn to simulations, we turn to designing simulators in order for us to append our observed data with simulated data and hope for us to make some good judgments. So with simulator-based inferences, then, there are a variety of components that we are bringing into play. So starting off, we have our real-world observations that I will denote by Z, right? And then in my particular case, I'm interested in investigating deterministic simulators. So outcomes from a deterministic simulator F, I'll denote as F of X, right? And then both of these things we're hoping to use in order for us to be able to assess certain features of the complex system, which we denote by Y, right? So effectively, what we're hoping to do is to combine information with the real-world data Z, with this computer simulator outcomes F of X, and we've done computer experiments. So we might, or I denote all of the runs by capital F, right? And we're hoping to be able to combine capital F, real-world observation Z, in order to learn about Y, right? So an example that we're going to use in order to apply the methods that we develop here is relative to climate change. So for an example, we would have, say, Z temperatures, temperature measurements in grid cells across the globe, Y representing or denoting the true grid cell temperatures. These are features of climate change, right? And capital F representing the predictions that we have from, say, one simulator for an atmospheric ocean general circulation model, right? Oh, and I forgot to say, you're welcome to ask questions during the talk if you so choose. All right. So the problem is that uncertainties in the simulator certainly limit us from being able to make certain kinds of inferences, or the kind of inferences that we really want to make about y. And when you have a deterministic simulator, so again, this is not stochastic, when you have a deterministic simulator, for any given input, you only have one observation. So you're stuck then with one observation trying to be able to differentiate what's signal from the simulator and what is error or noise within the simulator. The bonus is that in many of these, definitely these complex scenarios, there are a variety of agencies all trying to predict the same thing. So there are multiple simulators that we have that might have at least some common outcomes that we possibly could use. Right? And so across these different agencies, we're developing multiple simulators because there are competing theories, there are competing scientists, right? There are resources within each of the agencies that naturally result in multiple simulators to assess the same tough problems. And so then the natural question is, can we use the information across these simulators, across multiple simulators, in order to assess why? And being good statisticians that we are, the answer is absolutely, positively yes, right? And then a similar question would be, how can we model y so that the uncertainty in the simulators propagates then to, yes, oh, to the uncertainty assessments about y?
Sorry, I was just curious about your first point, the uncertainties in the simulator. Is that you're uncertain about some numbers that are going into that simulator, or you're uncertain about the logic being correct, or that it's capturing things right?
All of the above, right? So just as what Tony said, like every simulator is going to be wrong, right? Whether it be input values that we're using, whether it be the assumptions that we have, but effectively we're ending up with a prediction about y that we know has some uncertainty associated with it, even though it's still a deterministic model, right? So even though we don't have that variation there. Good question. Any other good questions? Okay. Fair enough. All right, so here we are. I'm saying that in many cases we have a variety of simulators, and what we want to do is to be able to use all of them jointly in order to make inference about the unknown. Right? And so for us, we determine the set of simulators as a multiple model ensemble. So in our case, we might have one prediction from each of these simulators, right? So let the researcher give me what they think is their best prediction for whatever the unknown outcome is that we're trying to learn about. And with that then, the MME might have M different models or M different predictions, all coming from M different simulators across the globe. And right now I'm just talking about in generalities, but each of these particular predictions, they could be univariate, but most likely they're going to be very high dimensional, either vectors or vectorized matrices. Right. So our particular example that we're interested in was presented with the IPCC. They called upon research groups across the world to predict aspects of climate under specific future scenarios. So each research group or each research agency was using their own climate simulators in order to make these predictions, and subsequently each agency provided them what they thought was their best guess for what future climate was going to be. Okay. So in this particular case, there were 20 AOGCMs, right, so worldwide. So a multiple model ensemble from the IPCC would have M equal to 20 different models. So common practice, however, when we're trying to learn about y, when we have both Z and a multiple model ensemble, is possibly to assume this conditional independent structure. And I'm not talking about, I'm definitely not going to get into the differences among the probabilistic assumptions that are being made, or rather the distributional assumptions that are being made. But fundamentally underlying each of these hierarchical or models to be able to learn about y is this conditional independent structure. As an example, though, you might consider something where the observations conditional on this physical process is normal with some sort of scaling of the unknown process and a variance. Actually, I've got this fancy color scheme. So you have an incidence matrix P, maybe a diagonal observation matrix delta, variance matrix sigma superscript j that reflects the simulator quality, and then possibly a simulator-specific bias that we might denote by mu superscript j. So fundamentals, aside from this conditional independence, fundamental assumptions that are underlying this common practice are two major points. One is exchangeability, and the other pertains to systematic bias or lack thereof within this common practice. So in particular, like I said, I like to go back to basics when it comes to my talks. We will remind ourselves what we mean by exchangeability, right? So exchangeability is saying that a sequence of random variables is exchangeable if the probability of any finite subset of random variables is invariant to permutation. The hesitation, however, is that each of our outcomes from a simulator might be extremely high dimensional. There could be thousands of quantities. And so what we're calling upon when we make these assumptions is that we can actually make the expert judgment that these vectors of thousands of quantities are fully exchangeable. And so we step back and we ask, can we really assume exchangeability honestly? Can we make a good argument to say that computer model outcomes are exchangeable among one another? The other key point within this common practice pertains to systematic bias. I get this particular, with that conditional independence, it's suggesting that any discrepancies between a prediction of a computer model and the real world are all uncorrelated, right? So if I were to define D superscript J as the real world process minus a prediction from any given model, what it's suggesting is that these particular discrepancies are a priori independent, right? And so then there's this natural question, then what if there's a systematic bias that's shared across all the different models, right? Oh, I thought there was another one. And so then the IPCC report actually addresses that particular point and recognizes that any variability in the simulator predictions, right, only explains a part of the simulator uncertainty. And it makes sense to me to think that they have common components that are either missing or modeling incorrectly. We are still limited by the knowledge of us humans. Every model is going to be wrong. So it's a natural assumption to think that how the models are wrong might have some shared components to it. So what we do for the rest of this talk is we're going to challenge those particular fundamentals. So for the remaining 20 minutes, right, we're going to go through the following outline in order to challenge those particular fundamentals. We'll start off with our methods, in that rather than assuming exchangeability, we're going to assume second-order exchangeability, which we'll discuss and define, and we'll learn that it's a much weaker assumption than full exchangeability. Right? And then also, we're going to be able to model Y that incorporates a systematic simulator bias within our analyses of Y. Being that we assume second-order exchangeability, however, that limits the kind of analytical procedure that we can use. So we take on the incorporation of Bayes' linear methodology, which was developed by Michael Goldstein up at the University of Durham. Right? And then we'll apply our methods to climate data, as I've already suggested, and then just have a one-slide discussion. So the first fundamental that we challenge is a matter of whether or not we want to assume exchangeability. And so we decide that second-order exchangeable makes a little bit more sense. Many of us haven't exactly heard about what that is, so let's again define it. So if we have random variables, f superscript 1, f superscript 2, up to, say, in principle, an infinite number, they're second-order exchangeable when only their first and second-order moments are permutation invariant. So that would suggest that each of the computer models might have a common mean, right? The variance for each of these particular computer models will be consistent, will be common, and then the covariance between any two computer models would be constant. So some comments about that is that when we're presented then with a multiple model ensemble, it's very possible that every model within that MME is not necessarily second order exchangeable. So it's up to us to be able to perform some sort of mental experiment in order to decide which ones we think are reasonable to be considered SOE and which ones we don't. Right? So examples as to why we might not think that every model is second-order exchangeable might be that we learn more about the tuning process from the individual agencies, or the complexity of the models are drastically different, and so forth. What's crucial is that second-order exchangeable assumptions are pairwise assumptions. So when I talked about having a mental experiment in order for us to be able to decide whether or not full exchangeability is appropriate, second-order exchangeable, to me at least, is reasonable. And the idea is that if we're given a multiple model ensemble, we randomly draw two and ask ourselves, do we prefer one prediction over the other? And oftentimes, well, in some cases, the answer will be yes, in which case they're not second-order exchangeable. But in other cases, the answer might be no, like I don't know which one to pick, right? And you draw another two, and draw another two, and subsequently perform this mental experiment to decide whether or not the set of that you choose is actually second-order exchangeable. And so with that then, second-order exchangeability, even these high-dimensional situations, is at least easier to conceptualize than possibly full exchangeability.
These F's are vectors. Exchange the entire vector.
Correct. No, that's true. That's right. Okay, and then the last point, and I'm really going to drive this home, is that both the exchangeable assumption as well as the second-order exchangeable assumption is made a priori. That definitely confuses people whenever I discuss it. We're not making this judgment after we've observed these deterministic simulators because they're deterministic, right? So their expectation is going to be equal to their result, and they're definitely not going to be the same. All right. So implications of the second-order exchangeability actually allows us to decompose each one of these estimates into two pieces that, again, to me, are easier to conceptualize. And we're able to decompose them using something called the second-order exchangeable representation theorem that was also developed by Michael Goldstein. And the idea is that each outcome can be decomposed into both a mean and a residual term. And this particular residual term is uncorrelated with any other residual that's created by the set that's second-order exchangeable, right? As well as independent of the mean term. Right? So with that representation theorem, the following applies, that the expectation of f is equal to the expectation of the mean, right? And we consider the residual to have zero expectation. The variance is then both the sum of the variance from the mean and the sum of the variance of the residual. In many cases, when people do these analyses, they actually fail to consider there's a variability about this underlying mean component from our predictions, right? And then the covariance then is, again, conceptualizable. It's a component that we, again, can be able to describe as the variance of that mean. So that means, so again, I'll just repeat the point that we can possibly make meaningful judgments about each of the individual f's because we've decomposed it in a very basic way. Right. We consider this m of f, or the mean component, to be considered a representative simulator. Right. So the mean of our predictions might be a natural estimate for this representative simulator. And then the sample variance, however, is only an estimate for the residual variance, right? Again, the sample variance is not at all containing any sort of variability that could be consistent with or could be related to this representative simulator. All right. So the other particular fundamental that we were challenging was the incorporation of some systematic bias. So for us, and we take this particular modeling approach, where the unknown features of the physical process are a function of this representative simulator, maybe scaled, say, by matrix A, right? And in many cases that just choosing A to be the identity can work out just fine, right? And then also, though, summed with U, which is the uncertain, uncorrelated with F, systematic bias. Right? And then a natural assumption might be that this particular, oh, you can't see the colors up there. But what might be is that the expectation of U is 0. When we decide to then just model Z with a similar structure for a model, then we're actually changing that conditional independent structure so that no longer do we have F conditional on Y, but each of the F's are conditional on this representative simulator, as well as the underlying or the unknown process conditional on this representative simulator. So just another comment about that is that we're saying then that the physical system or the physical features of the physical process actually respect this exchangeability property. So implications of this choice of model are as follows, right? Let's go back to that definition of discrepancy. Based on how we define our Y, that's again the features of the physical system, and how we define our F's, then we're left with this clear separation for the differences between reality in each model as this systematic bias minus this residual component. Okay. So when the expectation, the U is irrelevant, right? And the expectation for the discrepancy between any model and reality is still 0. But the variance, however, is a component for the variance of U and the variance of the residual. Similarly, right, the covariance then between the discrepancies for each of these individual predictions and the reality is also the variance of U. Okay. So we are then, within this particular, arguably simple modeling approach, we're accounting for the common biases across the simulators. Right. And then we'd also like to point out there's the natural relationship then between the mean prediction across all of these simulators and y is well defined. Namely, the expectation for the mean simulator, right, and reality is 0. But the variance then between y and the mean simulator is going to be the sum of the variance of u as well as the average for the variance of the residuals. So the more simulators you get, what people really want, the more simulators they get, the better we're going to be able to predict y, right, which is true in expectation, but we'll never actually be able to reduce our uncertainty to 0. Right? Because we're including this particular component about u, right? So there will always be this underlying uncertainty about our, within our inference, right, that's based on that systematic bias. So, but then also, though, if we do set that to 0, then you can probably think of it as we're saying that the true climate is very similar to this representative simulator. So if you as an expert really believe that, then even with our modeling strategies, you can still incorporate that. Okay. All right, so as I mentioned to you before, because we're dealing only in the second order exchangeability, that limits us from doing just a fully Bayesian approach or a fully probabilistic approach. So we are left to use another paradigm known as Bayes linear, right? So we assume second order exchangeable, not fully exchangeability to model y, right? So, sorry, I'm just repeating. We can't use fully Bayesian methods. What is Bayes linear? Bayes linear is a technique that adjusts prior moments, right, not probability distributions given data. Two fundamental equations then within Bayes linear are the following. Is that if we have a random vector A, right, and data B, right, when we specify prior expectations and prior variance for the joint of A and B, then we have what we call adjusted expectation of A given B, that's this first line, takes on this particular quantity, and the adjusted variance for A given B takes on this particular quantity, right? And these quantities are heavily reliant on our prior joint expectation and joint variance between the data and the unknown quantities. Okay. So in our case, right, the unknown quantities is related to the physical or the features of y, right? And our data include both the real and the simulated data sets, right? So A is y, B is the set. And so inference then is based on our just expectation for the physical system given the z and f, right? And our adjusted variance of y given z and all of our predictions within our second order exchangeable set. Crucially, Bayes linear is an extremely subjective approach, so we have to be smart and think hard about what we think our prior joint expectation and variances are for the unknown quantities and our data. Okay. So an application now, as I said, we're going to apply this to the data that we obtain from the IPCC, right? So we're going to assess global surface temperature, right? Where we have observed and simulated predictions taken from the World Climate Research Programme's data repository. In particular, we're going to be interested in just in assessing the winter surface temperatures from 1980 to 1999, right? And within this particular data set, there are 20 tuned simulator predictions. These predictions, again, are grid cells across the globe. That's 72 by 34 grid of the globe. Then when we vectorize this particular matrix, then we're left with a 2,448 element vector. Right? And the real data then were interpolated to match this particular grid. So to give a picture of what we observe, right? So here is a map where we have the temperatures obviously across. We see very high temperatures around the equator and so forth, cooling down as we reach the poles. And then what we have for white, those are missing observations, which come in handy. For our methods. Yeah.
What do you mean by winter?
So it's the Boreal winter. What is that? September through. I actually have it written down, but I know John. Is it September through November? Pardon? Northern winter, which are which dates?
December, January, February.
There you
That's
go.
okay. So you do mean winter in one hemisphere?
Yeah.
Yeah, okay.
Otherwise, it wouldn't be clear what you meant at the equator.
You're right. I'm sorry. That's a very good point. Any other questions? All right. Cool. All right. So here's our map of our observed data. And I started to say that the missing observations became actually useful for us and that we're going to make our predictions for those missing grid cells, as well as be able to account for what we think the uncertainty is with those particular predictions. So the analysis procedure is the following, right? The goal is to assess the true grid cell temperatures for Y given Z in our second order exchangeable simulators, right? So we have to select simulators S from our MME that we consider our SOE, right? Which actually reduces the 20 simulators down to only 14, right? We have to specify our expectations for the representative simulator and the variance for the representative simulator. And with that, we end up taking advantage of a simpler model, an energy balance model, as well as we specify a spatial correlation for the grid cells, taking advantage of a Matern correlation function, specifying a correlation length, and what we call zonal standard deviations. If you want to know more about that, we can talk later. We also have to specify the variance of these particular residual terms. And in this case, we have an over 2,000 element vector and only 14 simulators, right? So with the sample variance then in that case is not going to be full rank. So Jonty came up with a great idea to be able to fill out, if you will, a variance matrix that takes advantage of what we observe as well as what our experts might suggest for that variance matrix, right? Since again, these are expert specified quantities, we do end up checking, sort of validating our judgments, and with that we use a leave one out prediction of simulator outcomes, right? Then the next thing up, this is the variance of E that's in our model for the real world observations, and then you have our U, which is the systematic bias. We have to specify variances for that, right? And with that, we make some smart specifications, and again, when it comes down to the variance of U, we relate it back to what we thought our variance for the representative simulator would be, right? And then the last, I guess I thought it would go away. And then the last part then would be able to calculate, I swapped it. This should be the adjusted expectation of Y given these pieces and the variance of Y given those pieces. I'm sorry, I have an error in the notation here. But we're taking, again, the Bayes linear approach. We're aiming to adjust our prior judgments for these moments by the data we have. Right? And when we do that, we end up with the following map. We have our predicted surface temperature. So like I said, we filled in all of those missing pieces. And subsequently, we have a prediction error associated with those particular missing pieces, where cells with observation data ended up being less than 1 degree, but cells with missing data ended up being less than or equal to 2 degrees. And again, you have the scale here to be able to tell us. All right, so that's pretty good timing. So for a discussion, right, here we are. We're considering fundamental modeling. We reconsider fundamental modeling assumptions when it comes to being able to use multiple simulators to make predictions about the unknown. And specifically, we challenge these assumptions of exchangeability and the fact of no systematic bias, right? In particular, we can summarize what we did by, we assume simulator evaluations are what you say, second order exchangeable, and the physical process Y respects that exchangeability. Right? In our application for surface temperature, we use real world observations Z as well as an MME, right? And then with expert judgments to assess the mean and variance for the global surface temperatures in missing grids, right? We did not apply this method yet for future climate, but it's possibly to come. First, we have to get this paper out. The hardest part, though, most definitely is a matter of prior specifications. These are tough quantities to be able to assess. And so it requires definitely long conversations with our experts, right? And then there's the approach, then the one benefit of our approach is that it is very generalizable to say other seasons. Not just, right, not just January, February, or December, January, February. All right, so that's it. Thank you.
know what it was, since before today I don't really think I did. So, and just said, well, I've got all these model runs and I've got some data and I just want to match them up in some usual way. So I think of myself as having realizations from some massive selection of models out there, maybe even with a random effect, describing bias or not. So, but ultimately what I'd like to know is if second order exchangeability is never even conceptualized or is ignored or in fact is not actually something that's sort of violated by the way the whole thing is set up and the way I conceptualize it, how will I be led wrong?
If you don't have second order exchangeable, how would you be led wrong? Well, then you might be taking advantage, either if there are simulators in there that are more correlated than each other, then you might be able to take advantage of that information, right? You're more or less double accounting some aspects. Let me actually stop and think a little bit more about that question.
Or you've been living your life with no second order exchangeability.
I suppose we could pose the question, what if we didn't, so if we were to take the full exchangeable, what are we going to miss? And so you're left.
So the question is how you test out the assumption and the sensitivities.
I think is that true? How you test out, or what if we're wrong in our assumption? What's going to happen?
No, so I could imagine trying to set up a hierarchical model that would say, oh, here's a bunch of simulator realizations, and here's some data I'm going to match it to, and try my best to do that one way or another, or to make predictions or whatever I'm going to do, but. I guess I don't know where exchangeability comes into the way that somebody would formulate a setup.
Well, all right.
Where they would be led wrong if it wasn't correct.
If you had two models that were exactly the same, and your set that you're assuming are second order exchangeable, right? Then your variance estimate is going to be extremely small, right? And so then you're left with this particular problem of underestimating uncertainty because you've assumed that these two things are supposed to be different, but really they're the same. So things like that will come into play. Does that answer
Good question, yeah.
The U that is capturing stuff that we have no way of knowing that we don't know it. That seems to be a key quantity, and I wonder if you could say a bit more, please, about how you should come up with that, because I just don't see how you could quantify that, even though I think you should.
So it was very, yes.
Remind us what U is.
U is the systematic bias.
Systematic bias.
And ultimately, it came down to being able to cross-validate and be able to double-check our predictions to see how large or how small our prediction errors were in the end. Is that right, Jonty? Did I?
Yes, we made a bold judgment,
right.
And then we did detailed diagnostic checking.
Mm-hmm. But how do you check against? I mean, it's capturing things you cannot possibly know. So
well, you have the measurements, don't you? Which and the measurement, the variability of the measurements, the predictive mean and variance of the measurements incorporates U as a component.
In the real data.
Yeah.
Yeah, so we're using also a lower order model in order to be able to start building some judgments about the quantities that we would be expecting. So one difference is that we're really trying to make these prior judgments sort of unrelated to what we actually think the physical process is doing, right? We're talking about the expectation and the variance of the simulators, right? Not the expectation and the variance of the actual physical system. So there's this fine line that we have to mentally separate and not cross. Does that make sense?
This is a great discussion. Perhaps we can, we have various panel sessions we can return to these very important issues, but I think we need to proceed. Thank you very much.
Okay.